Nayan Moni Bashya, Yash Gupta and B.R. Manoj from IIT Guwahati.
Good morning, everyone. My name is Rohit, and I graduated from IIT Guwahati last year with a bachelor's in electronics and electrical engineering. Today, I am here to present my research paper on the project on the topic BiLSTM and attention-based modulation classification of realistic wireless signals. To give a brief outline of the topic, we'll first start with an introduction of what is modulation classification, and then we'll see the objectives and the motivation of this paper. We'll then talk in brief about the synthetic radio frequency datasets that have been proposed for the modulation classification topic. We'll then take a look at the proposed architecture that we have proposed that we call quad stream BiLSTM attention model. We'll then take a look at the experimental setup, the set of datasets and the experiments that we have done. We'll then take a look at the results and discuss it. To get started, modulation classification is the task of determining the modulation scheme of a radio frequency signal without any prior information. It has many civilian and military applications: cognitive radio, signal recognition, and spectrum monitoring, to name a few. There have been many conventional EMC methods. Decision theory and machine learning statistical features have been proposed for so long. However, there are some key drawbacks of these conventional methods, because with these conventional methods, the complexity of the model becomes very large. Also, they are not scalable in the sense that we need different models for different modulation schemes. Now, this is where deep learning comes into play. Deep learning can directly learn the features from the large-scale radio frequency datasets. It is efficient since the physical and signal models are even unknown. Also, it is highly scalable because we need only one single model for a variety of modulation schemes. However, developing accurate and generalizable deep learning models is very difficult because we need large-scale and realistic radio frequency datasets. This is difficult because obtaining real radio frequency datasets is expensive, because we cannot get the labels for each of the modulation schemes. To address this issue, synthetic radio frequency datasets have been proposed. RML 16, 18 and 22 are few of the benchmark datasets that have been proposed for the same. We have to keep in mind that our deep learning model doesn't become very complex. This is because as the model becomes very complex, it is difficult to deploy on the edge devices with limited storage capacities. For edge applications, deep learning models have to be optimized for faster inference, less storage, and power consumption. So what are the objectives of this work? We are trying to achieve state-of-the-art modulation classification accuracy on realistic signals. The goal is also to reduce the number of parameters so that the resource-constrained edge devices can be used. To achieve both these objectives, we are using complementary information from two different representations of the data. First is the in-phase quadrature data, and second is the amplitude phase representation. We use bidirectional long short-term memory cells and attention layers used in conjunction to capture the temporal characteristics of the data. Also, we are using parallel features which are extracted through 4 different streams, which will capture the spatial characteristics of the data. To talk in brief about the synthetic radio frequency datasets that have been proposed so far, RML 16 was the first of its kind. It was published in 2016. It had a dimension of 2 by 128, and it had 8 digital and 3 analog modulation schemes. This dataset was generated using the GNU radio. Then came the RML 18, which was published by the same set of authors, and it had the goal of capturing a wider scale of modulation schemes. This dataset proposed 24 modulation schemes instead of just 8. Compared to RML 16, it also captures the over-layer propagation effects used to generate the more realistic signals. Then came RML22, which is a recent radio frequency modulation classification dataset, which was actually proposed to address the drawbacks of RML16. It had a motivation to improve the data quality, to design more robust and generalizable deep learning models for real-world deployment. It consists of radio frequency signals of the dimension 2 by 128, consisting of 8 digital and 2 analog modulation schemes. It addresses the errors in RML16 due to incorrect signal-to-noise ratio computation and infeasible information sources for analog modulation schemes. Our work focuses on developing an accurate deep learning model for the RML22 dataset, which can achieve better performance on the real-world signals. This is our proposed architecture. It's called the quad stream BiLSTM attention model. The input RF signal is split into 4 data streams: IQ, A5, and the independent I and Q channels. The model consists of 2 parts essentially. First is the spatial feature extraction block, which will learn the spatial characteristics of the data. Second is the temporal feature extraction block, which will capture the temporal dependencies in the data. Now let's take a look at the spatial feature extraction block. Here we are using 1D convolutional layers used to extract the spatial features in the data. We are using 4 different streams: IQ, A5, I, and Q streams. The reason why we are using independent I and Q streams is because these are orthogonal and these carry complementary information about the signal. Features learned from all the streams are concatenated and passed through a 2D convolutional layer to capture the spatial characteristics of the data. These are further passed on to the temporal feature extraction block, which consists of 2 things. First, an BiLSTM layer, and second, an attention layer. BiLSTM is useful for extracting temporal dependencies in the time domain signal. Attention is applied on the output of the BiLSTM layer. Attention is needed because it captures the most important set of features produced by the BiLSTM block. This proposed QSL network implements dot product attention. At the end, we are using fully connected layers and softmax layers to predict the classification output. For the experimental setup, we are using RML22 dataset, which consists of 4,20,000 samples of the dimension 2 by 128. It consists of 10 modulation schemes, SNRs ranging from -20 to +20 in time steps of 2. We have split the training, validation, and test datasets in the ratio 8:1:1. We are using categorical cross entropy loss function along with the Adam optimizer. To talk a bit about the already existing architectures, first is the baseline CNN model, which was originally proposed for the RML22 dataset by the same set of authors. It consists of only one input stream, IQ. The second was the dual stream CNN LSTM architecture, which was originally proposed for RML16, but it is a benchmark dataset. It is a benchmark model, and it consists of 2 input streams, IQ and A5. Third is the dual stream BiLSTM attention model, which consists of 2 streams, IQ and A5, and it captures the temporal dependencies in 2 streams using a BiLSTM attention layer. The fourth and the fifth are the ResNet and the DenseNet, which are already quite popular in the literature, so I'll just skip over the details. Now on to the meat of the discussion, results. First, we'll take a look at the classification performance. As you can see, our model achieves state-of-the-art classification performance on the RML22 dataset. This proposed model achieves around 99% accuracy on the all the -20 to +20 signals. This is significantly better than all the previous models. This is an improvement of around 10%, as you can see. Now, if we take a look at the computational complexity, we are using fewer parameters than dual streams in LSTM, ResNet, and the DenseNet models. For an explanation of the DSBA model, we are saying that the DSBA model was originally proposed only for 6 modulation schemes, and hence it using the fewer parameters than QSLA. Also, in our set of experiments, we analyzed the effect of combining the BiLSTM attention layer. So we also tested with 2 alternative models. First, we only used an attention layer instead of the BiLSTM layer. So we are basically using 2 attention layers instead of BiLSTM and attention. In the second set of model, we are using only BiLSTM instead of attention layer. This is the computational graph between all the 3 models. As you can see, the proposed QSLA model requires not much memory. The only BiLSTM model requires a lot of memory and trainable parameters, and the only attention model is quite light. The accuracy results are quite interesting. If you see here, the QSLM model achieves the highest amount of classification accuracy. The only attention model achieves a good classification accuracy, but it has to be noted that it uses only fewer parameters than the QSLM model. From a classification performance, we are proposing the QSLM model, but if the number of parameters is to be kept as an evaluation metric, we are also proposing the only attention model. To conclude, we have proposed a deep learning model for AMC, which we call QSLA, and it uses the realistic RML22 dataset. We are using 4 input streams, I, Q, A, phi, I, and Q. We are using convolutional layers to extract spatial features. We are using a single BiLSTM layer and an attention layer to capture the temporal features of the data. The proposed QSLA model achieves state-of-the-art accuracy on the RML22 dataset. Deep learning models are vulnerable to various security threats, and as the future scope of work will analyze the robustness and the models developed for the RML22 dataset against such threats. Thank you.
We have time for a couple of questions.
So before applying this IQ samples or amplitude phase samples, like, are you pre-processing it? Are you doing any other transformation? Because these are very low values, right?
Yes. So we are not normalizing, we are not doing anything. We just split the IQ samples into.
So whatever is there in the radio ML dataset, you are directly
Yes.
feeding them. And like, what modulation classes you are classifying? Like, I mean,
So we have around 10 modulation schemes that we have, WBFM,
okay.
and we have a long list.
Oh.
Any other questions?
So input circles I into you take as orthogonal. So it is your convention, or maybe non-orthogonal case may be applicable.
The input signal is of the form I plus JQ, so they are orthogonal in their representation.
Thanks.
So the metrics that you showed for the final network, right? Like, so I'm assuming these are for this one as well as the accuracy metrics. I think these are for the weights being double precision and so on. So any comments from your side on when you actually deploy this on the edge and the precision comes down, what's the loss in accuracy?
We haven't tested yet by deploying, so that's a future.
Let's thank the speaker once again.